Thank you, Michael. So Stefan and I are actually going to continue a bit on the theme of code reuse that Alan nicely set up. So code reuse, as Heather mentioned in her talk before, actually is one of these kind of perennial holy grails of computer science. We computer scientists have been trying to get people to reuse more code forever. And I see this as kind of like us trying to get people to eat health food sometimes, because this is something that's good for you in the long run, right? Having lots of reusable code available makes a language ecosystem healthier. It provides lots of value in the long term, so we want that to happen. But it's not necessarily to your short-term benefit, right? People want to eat something that is tasty and cheap. And the analogy to programming, in my experience, would be that programmers basically want code that is easy to write and that runs fast. Programmers will do a lot of things. They might, on a good day, do other things too. They might write code for readability or maintainability or testability or all sorts of other things they might do, but the things they will really, really reliably do, in my experience, is easy and fast. They will do whatever it takes to figure out how to make their program run fast. They will do basic science on your language. They will compare things. They will look at the implementation. Whatever it takes to make their thing run fast, they will find it, I promise. Right? So that's kind of, as language designers, that's sort of a major driving force we're up against. So people kind of want to eat junk food. They want performance, and they want their life to be easy. How do we get them to eat healthy? So we think in Julia we actually have an unusually large amount of code sharing and code reuse. I think we're actually kind of constantly surprised or impressed or something at how well this seems to work, and I'll show an example. It can be even a bit difficult to believe if you haven't kind of used the language and been involved in it. So we're going to talk a bit about why we think we have a lot of reuse and kind of drill down on what's going on. Is it possible we have made Cheetos that are good for you? We'll see. So here's an example of the kind of thing that happens in the Julia ecosystem. So here is a small piece of code that uses 3 Julia packages. So there's diffieq package, which is Chris Rackauckus's package that Alan was talking about, which is a really big and sophisticated suite of differential equation solvers. I think it's really pretty much the best differential equation solver suite out there. It really is very, very impressive and comprehensive. And then there's also this nifty Julia package called measurements, which if you see in the top line there, it provides a plus or minus operator. So you can say g equals 9.79 plus or minus 0.02. And that will give you an object that represents a quantity with some measurement error around it. All right, so there's that. And then there's plots, which is just the plotting package. And you can just bring all of these in and use them together. So I set up an ODE problem to solve a pendulum. But instead of putting in normal numbers, I put in these measurement things. And I just run the ODE solver. And it just works. And I get out solutions with error bars. And then I can put that into the plotting package, and it just plots it, and it just works. So this is kind of amazing. I feel like this is something you don't see very often, this level of kind of interoperability of things naturally working together. And in some cases, things like this people have just tried them when the authors of these packages were different people, never collaborated with each other, and you just tried to use things together like this, and it just works. And it should, of course. All of us want that to work, but in reality, to see it actually happen, it can be kind of amazing. All right, so it's a little surprising that it works that well, but it's not entirely surprising. So Julia is based on multiple dispatch, and that is a paradigm that naturally lends itself to expressing generic algorithms. But there's a little more going on than we anticipated. So we did intend Julia to be for writing this kind of generic code. But we learned a lot of things over time. So we see basically 2 kinds of code reuse that happen. And this is this is actually a general pattern in lots of programming languages. These are kind of two axes of code reuse in general, not just in Julia. Where first you have generic algorithms, so you write out some code, but it can be applied to different types by basically substituting in values of different types. And then the other kind is you can have common data types, and you can add new functions that operate on them. And in the case of Julia, we can basically do both of these with the single mechanism of multiple dispatch.
Okay, I'm Stefan. We're going to be tag teaming a bit, going back and forth. So just to a little bit clarify what multiple dispatch is. So at a high level, it's defining functions with different argument types, and you can have different methods with where the argument types are different. And in dynamic multiple dispatch, the most specific method will get called. And so just to sort of clarify this, but also to address a thing that people often sort of feel like is similar, but it only looks similar and is actually quite different. This is different than function overloading, static function overloading in C++, for example. And I'm not picking on C++ here. It's actually a great language to compare to because it can do pretty much anything. It has lots of features and does lots of things and is very expressive. But similar features of function overloading and method overloading exist in Java and Scala and various other languages. But so this is a simple example. Here's some Julia code. It's a little contrived, as examples often are, but you have an abstract type pet, and then you have concrete subtypes cat and dog, and they both have name fields. And then you have this generic function called encounter, where two pets encounter each other, and it calls a function meet to figure out what the verb is that happens when they meet, and then it prints a line that says, okay, well, the name, the pet with this name meets the pet with that name, and some verb ensues. And then we define the actual methods for the particular combination. So if a dog meets a dog, they sniff each other. If a dog meets a cat, it chases the cat. If a cat meets a dog, it hisses, and if a cat meets a cat, they slink around each other. And then this is the actual usage. And here I've just defined these objects, two dogs and two cats. But in practice, this may be loaded from like a data file or a database, or specified by the user on a command line or something like that. So we don't necessarily know these statically. And then you just call, you have them all encounter each other in various combinations. So a dog with a cat, and a dog with a dog, etc. So same thing in C++. We have a class. We have this fallback function, but that we don't want that to be called ever, but we define it because it keeps the compiler happy. Same thing, generic encounter method, takes two different pets and then does something. And then we have concrete subtypes for dog and cat, and then we have our four methods again. So it's all very similar, but different syntax. And then again, the calling code. And in practice, the types are not necessarily statically known. So, okay, we're gonna do a showdown and see what happens here. So you run the Julia code and you get kind of what you expect. And then for the C++ code, does anybody have any prediction about what's gonna happen? Same or different? Okay, yeah, I mean, I'm in the right crowd for people to guess this. So it calls the fallback method every single time. And so, the why is pretty straightforward. If you understand what it means for the overloading to be static, it means that it actually only picks what method to call when it calls meet based on the static type information, which is its two pets. That's all it knows. So the key insight here, and this table has got a lot of stuff in it. It's kind of got the syntax of calling a function versus single dispatch versus multiple dispatch, what you're dispatching on, and then the expressive order, which is like how many things you're actually selecting code based on, and the expressive power. And the key thing is that, okay, when we're doing static overloading, we're on the top row. There is no additional expressive power. It's the exact same as rewriting the thing to have differently named functions. So single dispatch is nice because you get a little more expressive power because you're dispatching on one of the arguments, and so you can take a a static situation and get a little bit of dynamism. But in multiple dispatch, you get sort of an exponential amount of expressive power. Okay, so I'm going to hand it back to Jeff to talk about generic code.
Thank you. Okay, so here's a kind of a longer, slightly more realistic sort of worked example of how the sort of generic code story in Julia works out in practice. So here's a function somebody might write, inner sum, which takes a matrix and a vector of vectors, and we start with some 0, and we just for each vector we do this vector matrix product v times a times v for each vector, and just sum them up. So that inner function there is just we can show a simple implementation where first we do a times w matrix vector product, and then we do dot with the other vector v. So this will work on any sort of matrix or vector. So this is sort of the basic thing we're trying to compute. And as we say, yeah, so if you want this to be generic, just that's it. It already is generic. You don't have to just leave off any sort of type information. Nothing in here is constrained. It's basically duck typed like Python. So you can put anything in there. So the code is by default very generic. Just to show it works, I can make a random matrix and get a vector of vectors, and I can call it, and it computes a scalar as you would expect. So the code works. I said it's generic, so any matrix or vector object that supports the right operation will work. And as you pass in different implementations of matrices and vectors, you'll get whatever an efficient implementation is for those. So for instance, one nifty package we have in Julia is the static arrays package, which is arrays that are specialized by their size, right? Which is something that's you sometimes want and you sometimes don't. If you have arrays of size 1 million, 1,000,001, and 1,000,002, and so on, you don't necessarily want specialized code for every size. But if you have arrays of size 2 and 3 and 4, you might want everything to be specialized on the size. So this is, if you need that, you can use this package. And when you use one of those, basically, at the end of the day, you get machine code generated that looks like this, and it's basically just a totally, fully unrolled sequence of vector instructions if you happen to substitute in one of those. But it also will work for new types, and which could be even more efficient. So one really neat example I like is this kind of vector that comes up in machine learning that they have this very colorful term for, a one-hot vector. Which is a vector that is 0 everywhere except it has a single 1 in it. So it's used for encoding things in machine learning a lot. And this can be represented very compactly. We don't need to store all of the zeros. And all the information you need is the length of the vector and the index that has the 1 in it. Right? So here is a Julia implementation of it. We just say that, okay, there's a struct that's a kind of abstract vector, and it needs to have a length and an index that has the 1. And then you just define the size to tell us how to determine the size of the array and how to get an index, how to do indexing of it, and that's it. All you need is those 2 definitions, and then this thing will completely work like an array, and everything will work. So just to show that this also works, I can make so in fact you can basically copy and paste that slide into a Julia prompt, and then that's all you need to do, and all this stuff will go through. So it's actually kind of neat. We can construct these, and you'll see they get printed like normal vectors because all the printing code is generic and everything just works. And we can call an inner sum on it, and that also works. So any sort of vector operation will already work on this thing. But it is using the same algorithm that I wrote back on the slide where I defined this inner sum function. So it's still doing the thing where it's looping over everything. And it's not calling any functions that know about the special structure of this vector. It's all it has is that getIndex method. So it just individually has to fetch all of those elements, and nothing else knows that it's going to get zeros most of the time. So just to break down what happens here, so when I call inner sum, it's going to call inner, which is going to call that general method that calls dot and star. The star is going to call a generic matrix vector product function, which will iterate through the columns of the matrix and iterate over the vector. And dot is going to call a generic dot implementation, which just iterates over the elements of the vectors. But for this particular vector, you can do much better, right? You can, in this case, star for a one-hot vector is very easy with a matrix because you just need to select out a column. So we can add a method for that. So we can put in this definition, and then everything's going to get faster. But in fact, we can do much, much better than that because we could also define this inner function for it. And so in this case, since we're multiplying vectors on either side of the matrix, it really just amounts to selecting out a single element of the array. So instead of doing any kind of iterating at all, we can actually just pull out one method. And here are the results. So if you can do this and time these things, and it shows what you get initially. And so you can see there's, from specializing the star function, you get about an order of magnitude. And then when you add the extra specialized inner method, at this point, then there's no looping of any kind anymore. It just pulls an element out of the array. It gets super, super, super fast. It's just, it's just a memory access. So there's this kind of something interesting happening here, which is, a lot of languages make a distinction between kind of the interface functions that you implement when you're defining a new kind of object versus sort of top-level functions, which are your kind of generic algorithms that call into those. And the problem with that is you don't necessarily know ahead of time which thing is going to need to be the interface function and which thing can be the top-level function, right? Because in this case, we got this huge performance gain by specializing this the inner function, which is not, that's not a normal like interface function for arrays. Like not every kind of array needs to implement that. You certainly don't need to implement that to have something work as an array. But in this case, to get the performance, we did need to implement that, right? So if we didn't have the ability to just have everything be kind of on equal footing as multiple dispatch generic functions, some programmer would get stuck in this situation where they can either do the generic thing or they can get the performance, but they couldn't get both. And so by the way we do it, we can get both. And that's kind of the point. I think I just said this. All right, so one interesting question about a system like this is basically how do you handle higher order functions? So in a lot of generic function or multiple dispatch systems, you have the classes, like the different kinds of objects, and then you have the generic functions, and they dispatch on the arguments. And the generic functions themselves, like, well, what are those? Well, those are just some special kind of thing. Generic function is just an object that does this calling thing. But in our case, we actually have generic functions have their own types. So we do something very similar to what happens in Java, for instance, when you have an anonymous function. Basically, per function, we generate a class, if you will, to use the terminology other people would use. So in Julia, if you have say the minus function here, if you try, what is the type of the minus function, it just prints out type of minus back at you. Actually, internally there's some kind of compiler-generated name for this that's not very readable. So we just print out kind of the easiest to understand representation, which is just, well, it's the type of the minus function. If you did plus, it would be type of plus, and so on and so on. So that basically lets us identify and distinguish functions the same as any other object, which is very, very useful, such as in this case, where I have 1:3, which is a basically special range type, which gives you a special kind of vector that represents the values 1, 2, and 3. But of course, more compactly, just like what we did for the one-hot vector. And broadcast is an operation like map. So it's basically just map. It applies the function to every element. But if you have multiple arguments, it repeats array elements and stuff like that. But for one argument, it's just the same as map. So if I do broadcast minus, this is going to be calling single argument minus, which is negation. If I broadcast minus on that, I need to get -1, -2, -3, and indeed it does that. It's able to return another range object, -1, stepping by -1, ending at -3, right? But that can't work for every function, right? If you map an arbitrary function over a range, it can't necessarily be represented as a range anymore, of course, right? Like if I do sine of 1, 2, and 3, that's not a range anymore. That's just 3 crazy numbers. So with sign, we actually have to return a dense vector where every element is stored. But for minus, we can do something special. So someone has actually gone in here and specialized broadcast of minus on a range, and for a few other functions where a similar kind of trick is possible. Thank you. Here's an even fancier case of where someone applied this trick. So we have a very general function find first for finding the index of something in a collection, and it basically takes a predicate and a collection, and it gives you the index of the first thing where the predicate returns true. All right, now we also have this ability to call a comparison operator like double equals on a single argument, and if you do that, you say double equals of 2, it will basically return you an object which is that function with the value of the second argument fixed. So we produce this object. You can see the type of it there called fix2, which just means it's the equals function but with the second argument fixed to something. So equals 2 gives you a function that compares its argument to 2. So I can pass that to find first. And if we can say at which to ask Julia what method it will call, and it prints out the specialization. So apparently there, we've implemented a case of find first where there's a predicate, and the first argument can be a fix2 of either double equals or the is equal function, which is similar. And then the second argument is a step range. So in this case, of course, we're looking for a number in a range of numbers. So that can actually be order 1, because we can just do arithmetic to find where that number would be in the range. And that's what it does. So this is kind of a really powerful form of dispatch where we can detect that somebody is trying to look for a certain number in a certain collection. And so basically what's happening here is there are kinds of collections that can implement find first efficiently, but only if they know what the predicate is doing. If the predicate is a complete black box, you can't optimize it. You have to just sort of try it on every element. But if you know something about what the predicate does, you can optimize it. And so being able to hook into that, it's another case where we can kind of preserve the possibilities of performance without dropping this really generic find first of an arbitrary predicate interface. Yeah, question?
Is it possible for me to assign this double equal to a variable and then pass that as argument?
Yes, yeah. So the double equals 2 returns a first class object. Yeah.
But wouldn't that require you to have the dynamic information to know what is the actual value of this particular variable?
Well, we need to know the type of it, actually. Actually, can I pull up a terminal? Let's just try that. I think it'll be clear if we just show it. Yeah, so just call that double equals of 2. Yeah, so it says it's I guess a type of that. Yeah, so that returns an object. And yeah, so that returns an object of type fix2 of type of equals and then int, which is the type of the value in it. So anywhere that object goes, that information goes. Yeah, so it's first class, yeah. We would certainly never do anything like, textually seeing that equals 2 happens to be in your program. So, no, of course not. No, heaven forbid. No, it's first class.
I guess it's my turn. Okay, so that's writing generic code and how multiple dispatch lets you patch into very specific pieces of a generic algorithm very seamlessly. But the other type of code reuse, sure.
The dispatch is type-based, is that?
Yes, yeah.
But you don't have to write types. I mean, these generic functions are sort of untyped. Is that?
Yes.
Yeah, so if you don't mention any types, the default type is any. And so that's the least specific definition. So if you write a definition of a method with no type specified, and then you write a definition with some type specified, the one with type specified will get called.
You cannot dispatch on particular values. It's always typed.
There's a special parametric type that lets you force things into the type domain, which is sometimes useful, but in general, no, it's type-based. Of course, with functions, each function object has its own type. So it is value-based for functions as a sort of special case, because it's so useful to do that. So the other type of code reuse is sharing common types, and this is actually the more surprising aspect of this, because we picked multiple dispatch for the ability to write generic code and have it work. So this other sharing of common types thing is really more the thing that caught us by surprise. So the example I'm going to talk about it's a pretty basic one. And it's real. This actually happens in our ecosystem, and is a good example of it. Is, suppose you have an RGB type. So there's a color types package which does in fact define a RGB type along with many other things, but it just bundles. It's a struct. It bundles a red value, a green value, and a blue value. It's that simple. And it comes with some basic operations, because there's some things you might want to know about a color type, like you might want to ask what is the value of the red channel, which makes sense for an RGB type and is easy to compute. It's a little harder to compute for like a HSV value, but you can still do it, and it makes sense as a generic operation. So those kinds of operations are all bundled together with the definitions of these types. But suppose someone else comes along and is like, okay, great, this RGB thing is nice, but I'd like to add some more operations. And in Julia, this is a simple thing to do, and here's an example. This color vector space package adds sort of slightly questionable from a color theory perspective vector operations on RGB and HSV and CMYK types, and it's slightly sketchy because you actually have to do some normalization and go through another type. But approximately you can just add them like they're vectors, and this and it's very fast, and this package does that. So in Julia, the way this works is that this color vector spaces package just adds some methods, external methods to the RGB type, and it just you just call it. So for example, to add a zero method, so it doesn't necessarily make sense to ask for the zero of the RGB type unless you're considering it as a vector space. So it adds this method for a standard library function, which is the zero function, and the RGB type. And it says, okay, well, RGB, the zero of the RGB vector space is all zeros. But it also works for new operations. So let's say you want to define a new .c operation, which is a sort of a dot product on colors. Then you can define it this way, and this is some sort of normalization constants that have to do with your perceptual, how you perceive colors. And you can do that as well. Okay, so what's the big deal? That seems like totally trivial stuff. And the question is this actually harder in other languages? And the somewhat surprising answer is yes. And especially in class-based object-oriented ones, which I'll call CBOOs for short, because it's kind of a mouthful. So in CBOO languages, methods go inside classes, right? We've all used these types of programming languages, and I mean they're like literally textually inside the definition of the class, which seems like it shouldn't matter that much, but it actually is kind of a problem, because now what happens if you want to add more methods to the RGB type? You have two options. You can either edit the original class, or you can inherit from it and add methods in a subclass. And both of those are not great, actually. So adding every method that anyone ever wants to add to RGB types is problematic because, first of all, you have to write to the author and convince them that this is a good idea. And they may not want to do that because they then have to maintain your code, which is not something people generally want to do unless they're like really convinced that it's a great idea. But if I'm like, this vector space thing is a little sketchy, maybe we don't want to do that. So they could just say no. Even if they say yes, then the class, can end up being really unwieldy because if, 20 different people wanted to add 20 different things and they said yes to all of them, now you have, all of this stuff crammed into the class. And of course, the thing is, if you change your mind at some point, if you're like, oh yeah, that vector space thing was kind of a bad idea, and actually color vector spaces is an abandoned project, so like it was a bad idea, nobody uses it. And now, if you had stuck it in your class, then you're stuck. You now have to maintain it even though you changed your mind. Whereas in Julia, because it's external, if you don't load color vector spaces, you don't get those methods. And so there's no problem. So let's say you wanted to do the way OO languages tell you you're supposed to do this, which is inherit from the RGB class. Okay, we can do that. We can then add methods. So the first problem and this seems kind of trivial, but is that you need a new name. And this is kind of annoying because now I need to call it my RGB when all I really wanted to do was talk about RGBs. I didn't add any data to it. I just wanted to add a method. That is all I wanted to do. So why do I need a new name? Okay, so all right, let's say I suck it up and I'm like, I'm gonna use this new name. It's sort of annoying. I'll just talk about my RGB objects everywhere. Well, the problem is now my operation still won't apply to plain RGB objects that other people created. So there's all this code out there that also uses RGB types, maybe generates arrays full of RGB values. I want to apply my operation to it, but I can't because it's not my RGB object. Same data, but I can't apply it. So then you end up with things like, hey, can you please like do this dependency injection thing, and I want to thread the type of RGB value that I actually want to get out of your generic code. And things, it's doable, but it starts to get kind of ugly and awkward pretty quickly. And of course, then if you have multiple extensions, so let's say one person adds, creates the my RGB type and someone else creates the your RGB type, and I want to use both of their method extensions, then I need multiple inheritance, and that's a complication, a new name, and also some languages may not even support it. So that's also not ideal. So we kind of have two lousy options to choose between. There's actually two more options, but they're even worse. So one of them is give up on dispatch entirely and just write an external function called, and just call it as f of x comma y instead of x.f of y. All right, well, that's nice in that it's external, but it's terrible in that now we don't get generic code at all, so we've totally given up on generic code reuse. So we gave up on the other half of the talk, which is unfortunate. And then finally, and I think this is the worst option, but it's also the one that people probably do the most in this situation, which is just you give up on code sharing, and you copy pasta the RGB type, and you make your own RGB type and add some functions to it. And we see this a lot. I think we see this in a lot of OO code bases and ecosystems. So what the key capability that Julia has here is like it's almost mind-numbingly dumb. Like what makes this actually work? And it's just that you can define methods on types after the type is defined, outside of the textual body of the class. So this is just external dispatch. That's kind of how we refer to it. There's other languages that have similar features, like Go kind of does this with their interfaces, and people seem to like that. I think that C# has a similar feature with external methods, but I don't know if they're dynamically dispatched. I don't know. Class? Well, in class you can do anything, so. So there's an additional subtlety, which is that generic functions are properly namespaced, unlike methods in a CBOO, right? So if you have two classes and you have multiple inheritance and they both happen to use the same name for a method, there's a collision. Whereas with external generic functions, it doesn't matter. Like, I don't care, because my package.foo and your package.foo are totally unrelated functions, and nobody cares that they're both named foo. It doesn't matter. They're different objects. Okay, and so then I think the final section we have here is about the expression problem, and Jeff's going to talk about that.
I am?
Oh, I guess I can talk about it. I think we're going to tag team the final section.
Yeah, go ahead.
Okay, so the expression problem, which people in this room may well be familiar with, but I'll sort of state it here. My favorite statement of it is from Mats Torgerson, who did a lot of work at Microsoft on C#, I believe. He talked about the expression problem revisited. So it's the degree to which your application can be structured such that the data model and the virtual operations over it can be extended without needing to modify existing code, without the need for code repetition, and without runtime type errors. Yes?
Are you going to say something about the implementation
Of this?
Yes.
I can afterwards. We can definitely talk about it, yeah.
Question after, yeah.
So basically, the question, to simplify this, it's can you easily and unsketchily do both of the following things? Define new types and get existing operations to apply to them, and then define new operations and apply them to existing types. And these have kind of a duality about them in that, one of them is easy in object-oriented languages but hard in functional, and then vice versa for the other type. And what we've noticed is that these are both, this is known, right? Like multiple dispatch is one of the solutions to the expression problem. That we didn't invent it or make that observation for the first time. But it makes both of these straightforward, right? So to define new types for existing operations, you just, you add new methods to your existing generic functions, and for the other side, you just add new generic functions to existing types, and they're both kind of trivial. And this is what allows you generic code, and this is what allows you shared types. So this is the connection to the rest of the talk. And so our conclusion is that solving the expression problem allows you to reuse code, and that's a very powerful thing in a programming language. Now, this is not the only solution. Multiple dispatch is not the only way to solve the expression problem. So, Haskell type classes also solve it, and C++ templates address this as well. Of course, only statically for the templates, and I think also for type classes. But one of the things I think we're trying to get at with the whole health food idea is that that convenience and defaultness are also really important, right? It's not enough to just solve the problem. You have to get the programmers to eat their vegetables. So if there's a big impediment to doing this thing, if you've written some code and you're like, okay, well, it works for my use case, why do I want to go add template parameters everywhere? That's going to be extremely annoying. So it probably won't happen unless there's strong demand for it. Whereas if you write some code in Julia, it's well, it's already a generic function. There's no other type of function we let you define. So that's the only thing you got going. So if someone else wants to extend it or patch into it some way, they already can. So I guess this is the idea of maximal applicability. All functions are generic, so it's the default. It's ubiquitous because it's fast enough to just be used everywhere. And it's first class in that functions themselves are even something you can dispatch on. So there's no boundary anywhere. There's no stopping point where suddenly you're stuck and you can't use this mechanism. And that lack of boundary is a very powerful feature of the system. And I guess we see that Julia programmers are writing reusable code, so the people are eating their vegetables. So that this makes us happy as programming language designers. So I mean, people may want to say, can we prove it? The answer is no. This is totally anecdotal. We don't actually know how we would measure this. So if anyone, this is a good conference to ask this question. If anyone has any good ideas for how to measure code reuse in an ecosystem, we're all ears. I would find that very interesting. It's possible that we're deluding ourselves, but we don't think we are. This does seem to be real from what we see. And it's reinforced by periodically people come to us and they're like, oh, I just tried these two things together and they just worked, which never happens. But there are trade-offs, so this is not all, it's not all fun and games, and there are always trade-offs. So I think, what we've observed is that you can have two of these three things: separate compilation, efficient specialization, or code reuse. So a lot of languages is sort of the tradition of PL design have been like, well, we need to have separate compilations. And so they've chosen, 1 and 2, or maybe 1 and 3. Julia chooses 2 and 3, and C++ with templates is also 2 and 3. So as soon as you start doing template metaprogramming, you pretty much throw separate compilation out the window. But that's a very popular and powerful way of using C++. So we think that there's a pretty wide open area to do sort of more research and more exploration of the PL design space by sort of reconsidering the separate compilation axiom. Do we need to really have that as a principle of the first principle of the design of a language? But we struggle with this, right? So code caching is a problem for us, and code generation is a problem. So we do some caching of specialized code, but we need to do more. Some of that is just elbow grease and work. But some of it is well, if I use this thing with this thing and this thing, what the specialization, maybe, there's nothing you can do other than generate specialized code for that, and that's just going to take time. It has to be compiled at some point. So I guess we're going to conclude with maybe some lessons for language designers. So one, solving the expression problem is actually important. It enables code reuse, which is a real world consideration that we should care about. But it's insufficient just to solve it. it has to also be convenient and the default. So it can't be tacked on, it has to be easy, it has to be fast, it has to be automatic. Ideally, don't even allow doing it the non-extensible way. That's the best way to get people to write a reusable code is to not let them not do it. It may require sacrificing separate compilation, and I think that there's a disconnect between the PL design community and users. Like, users clearly are voting with their feet and using C++ with templates. People are using Julia even though we don't have separate compilation. So there's some users out there in domains that consider performance much more important than separate compilation, and so that's a lesson that we should take to heart. But we need research on how to do it better, and I think that's the conclusion. Thank you. All right. So you had a question initially, yeah.
Right. Well, I think you have said something about. You said something about. So how do you implement this?
The most important thing is a lot of compiler specialization based on types. So we do basically a data flow analysis based analysis that specializes code on types as much as we can ahead of time, but then we kind of will stop and execute and intercept calls and compile more. So we do JIT compilation and specialization.
All right, so you do runtime
Yes.
compilation.
Yes.
And so the fact that you don't have separate compilation means you have whole program compilation, or you do,
Yeah.
or
Well,
you do runtime compilation. Is that?
we do runtime compilation, but most users do it that way, yes. But by that, we basically just mean if you want to use a novel combination of two libraries, we need to compile something because we want to compile an efficient specialization of that combination.
But you do ahead of time compilation as well, or?
We can. So some people want to just compile their whole application, for instance, and ship it. So that's a much requested feature, and we can kind of do it, but it's that's sort of work in progress.
Okay. So as a comment, I have a language with some similar properties, as in
Oh, great.
separate extensibility, for which we always did whole program compilation. But recently we have developed an incremental compiler for this language that has an interesting pattern that may be
Okay. Yeah. Let's talk more about that later. That
Yes.
sounds great. Yeah. Yeah.
Thanks for the talk. So I was wondering about your external methods. This is extremely useful, and I'm glad to see it in Julia. But don't you also want to have data that you could add to the objects or to the classes from externally?
Yes. So that's yeah. I mean, it's a good point. We do kind of give that up. We can't do concrete inheritance. So sometimes people want that, but we want to be able to specialize on something and have the memory layout be totally fixed. So we give that up. Yeah.
Okay, but since you have given up on separate compilation anyway, perhaps you could do it.
Yeah, I mean, I guess we could. We could make our compiler even fancier and recompile more stuff, and we might be able to do it then. I guess, yeah. But yeah.
So I actually have a philosophical objection to adding fields by subtyping a concrete type. And so the objection is that either something is completely specified and you can instantiate it, in which case you should not be able to subtype it, or it is incompletely specified and you should be able to subtype it and add more fields. And so I think that languages that allow you to do both of the same things are actually conflating two different concepts. They're conflating the partially specified thing that you can continue to specialize and the thing that you can instantiate. And so there's a pretty common recommendation in OO languages that you do this thing where you say, oh, well, there's actually the abstraction, which I'm going to have a concrete instance of, but then I'm actually going to inherit from the abstraction to add more fields. And that avoids a lot of problems, and we just basically tell people to do that. So it forces you to call those two different, the thing that you can inherit from and the thing you can instantiate, different names. And that actually avoids a lot of problems. Like the whole notion of like final methods and final classes sort of goes away because you're like, well, yes, all concrete things are final. I don't have to tell you that, if you see what I mean.
Yeah.
Thanks for the talk. I was reminded of Ruby's open classes. To my memories, if I declare a Ruby class again, I can put up further methods into it. And also to my memories, at these peak times of the hype, there was this issue coming up then that there were different semantics put, and they actually this overriding was bounded by, well, people had different understandings, and like different modules turned incompatible with each other because they overrode the same method. So I'm wondering if you have observed the same issue, that, I don't know, maybe someone defined string multiplication string as, well, and there are various interpretations of this.
Yeah, so in this kind of paradigm, the one thing that we find is really important is that a given generic function has to have a sort of, well agreed on and understood abstract meaning of some kind. Everyone has to kind of agree on, in what sense are we using that term? Like what makes a valid method of plus or something like that. So there does have to be some kind of a social process there that there's some sort of agreement about. It helps a lot to have that, yes.
So there's a cute term for sort of violating things the way people in Ruby do monkey patching, which is like, we didn't coin it, but someone in our community coined it, and it's like caught on, which is called type piracy. And so the principle is that if you're going to define a method for something, you should either own the method or the generic function. So if it's your generic function, go to town, do whatever you want. Or if you own one of the types of the arguments, then also that's safe, because now no one else could accidentally be calling it. You can't be overwriting anyone else's functionality. So there's sort of this implicit rule that you should own, like, either the 0th arg, the function, or the arguments, and then you're okay. And if you violate that, you're committing type piracy, which, is sort of, it's just socially frowned upon. But people do it anyway because it's sometimes useful.
You don't restrict programmers to do it.
No, we don't restrict it. But also, yeah, I mean, having the ability to overload on other arguments, of course, it's not always applicable, because for some things, maybe everyone wants to overload on the first argument. So in that case, it doesn't help. But in some cases, the fact that you can overload on different arguments is a way to kind of get out of other people's way, and you're not actually clobbering them because you're overloading based on something orthogonal. So that sometimes gets you out of that. But, yeah. Yes, specificity. So that is important, and yeah, we have a method specificity algorithm, and we sort them by that, yeah.
I'm wondering whether you are familiar with common list object system?
Oh, yes, yeah, class, yes.
So most of the things you are talking about were solved 30 years ago, and why aren't you comparing this common list object system? What's the advantage of your solution?
Yeah, I think it would make a very good talk to compare Julia to Klaus and why we did the exact things that we did. I think that would be a really good talk, but it would probably be a separate talk. Yeah.
I could briefly address it. So there's a couple of distinctions. So one is that I think the performance of multi-methods in class is not the same as ours. We use this for like integer addition, right? Like everything is a multi-method. Another distinction is that you have parametric types in class, and you have multi-methods, but you cannot use multiple dispatch on parametric types. So that's a pretty significant limitation. We do that all the time. And then another one is that it's opt-in, of course, right? So if you have to say that you're doing a multi-method, it's a little bit of a different approach.
Yeah, so the big issue is this sort of pervasiveness. Like there are a lot of common list programmers who never use class. Some people don't like it, or and you have to basically get everyone to use it for everything, which is sort of the challenge.
All right, thank you. So thank you so much.